good lunch? How are we feeling? Are we feeling alert? Are we ready to listen to a math chat? I see some people coming to find their seats. Is everyone ready? Everyone?
For me? Yes.
Or Luis?
For me?
Oh, okay. Are you speaking?
Yeah.
Oh, okay.
Yeah, I'm the speaker.
Yeah, excellent.
Yeah,
Excellent.
nice to
Okay.
meet you.
Well, very nice to meet you. And Luisa Higueras Montaño from the Departamento de Matemáticas, Facultad de Ciencias-UNAM. She is going to talk with us today about a geometric approach to tensor products of convex sets via tensor norms. So let's all pay attention, please.
Well, hello. Good afternoon, everyone. I would like first to thank to the organizers of the event, and especially I would like to congratulate Vilker Bach on his 60th birthday. So congratulations. And well, the topic of my talk today lies at the intersection of Banach space theory and convex geometry. And this is a joint work with Maite Fernandez Unzueta from CIMAT. So my purpose today is to give you an overview of a problem that Maite and I were working about, a question regarding is it possible to provide a definition of tensor products of convex sets that retains the main features of the theory of tensor norms on Banach spaces. So to do this, I'll divide my talk in 4 parts. And the first one, I'll give you the basics results from the theory of tensor norms and convex geometry that I'm going to require. Then I'm going to introduce the projective and the injective tensor product of convex bodies. And in the third part, I will show you our results. And finally, I would like to illustrate you what are the type of results we are looking for. So let's begin with some notation. So as usual, the algebraic tensor product or the tensor product of vector spaces is, again, a vector space together with a multilinear map, which is called the canonical multilinear map, and is defined in this way. And the universal property of the tensors is that on the tensor product, we obtain linearizations of all of multilinear maps on the Cartesian product. So through the talk, this T hat will denote the linearization of a multilinear map. So more notation. So RD will always denote the d-dimensional Euclidean space with the standard norm and Euclidean product. The letter X will denote Banach space with closed unit ball Bx and dual space X star. And the space of continuous linear operators is between Banach space, is denoted as usual. And if we have vectors on the dual space, then their tensor product is again a linear functional on the algebraic tensor product that acts on simple tensors in this way. So, well, what is a reasonable cross norm? When we're studying tensor norms or norms on the tensor product of Banach spaces, the first type of norms are these ones that are called reasonable cross norms. And they are norms on the algebraic tensor of fixed Banach spaces with these 2 properties. So the first property tells us that the canonical multilinear maps must be continuous as a multilinear map from the Cartesian product. The second one tells us that products of linear functionals is again a linear functional, and its norm is bounded by the product of the norms on the spaces. So there's a more geometric way to represent or to understand these norms, that it's by means of the projective and the injective tensor norm. So given a vector on the tensor, on the algebraic tensor product, then the projective tensor norm is defined as this infimum over all of the representations of the vector. So notice that this property is related to the first one over here, because if we want a norm to be a norm, we would like to have, or we require a triangle inequality. So if we require this, then our norms must be domained by this or bounded by this quantity. So this norm is the biggest norm that satisfies this condition. And on the other side, the injective tensor norms guarantees that these products are continuous linear functionals with a norm bounded by 1. Okay. So in terms, and this definition comes from this other one condition. So now we can define alternatively reasonable cross norms in terms of the projective and the injective tensor norm. So we say that a norm is a reasonable cross norm. It satisfies these inclusions or these inequalities. And the inequalities in the previous definition must be actually equalities. So what is a tensor norm and what is the main difference between them? So a tensor norm is an assignment that takes any L tuple of Banach spaces and gives us a norm on their tensor product that satisfies two properties. The first one is that we require that the norm be a reasonable cross norm, which means this. And the second one is a uniform property. So we want that tensor products of continuous linear operators are again continuous linear operators on the corresponding tensor product spaces. And their norm is bounded by the products of the norms. So here we have additional notation. So to simplify, the index here, alpha, denotes the normed space obtained by endowed the algebraic tensor product with the corresponding tensor norm. And the hat here means this is the completion of the tensor product. So now we move to convex geometry. So by a convex body, we mean a compact convex set with non-empty interior. If, in addition, our convex body is origin symmetric, then we call it centrally symmetric or simply origin symmetric. So there are some pictures of 2- and 3-dimensional origin symmetric convex bodies. So this is a classical and well-known result on finite dimensional spaces. It's a result from Minkowski from the beginning of the 20th century, and today is first propositions when you're studying finite dimensional spaces. So Minkowski proved that there's a bijection between origin symmetric convex bodies and norms on RD. And the bijection is given by this functional, which is called the Minkowski functional. So in this way, if this is a centrally symmetric convex body, then GQ is a norm with closed unit ball Q. And if we have a fixed Euclidean structure or scalar product, then the polar is the closed unit ball of the dual space. So we can represent, so polar sets, so this relation between between this convex body and its polar allows us to represent dual spaces on finite dimensions in the same RD. So what do we want? Our question, is it is possible to provide an intrinsic definition of tensor products of convex bodies having the origin in the interior compatible with the theory of tensor norms? And what do we expect from such definition? Well, we would like to have a Minkowski type theorem that allows us to, given a tensor product, we obtain a tensor norm and on finite dimensional spaces and vice versa. And we also want to preserve the calculus of tensor norm. So in order to do that, we are gonna fix the Euclidean structure or the scalar product on the tensor product of Euclidean spaces. So we have this object here, which is called the Hilbert tensor product of Euclidean spaces, and it is determined by the product of the scalar products of each space. So this scalar product actually determines a reasonable cross norm on the family or on the class of Euclidean spaces or on the class of Hilbert spaces. And we denote in this way the Euclidean ball of this space. So if I am on a tensor space, then polarity is calculated with respect to this scalar product. And with that, so now I have a natural scalar structure or Euclidean structure. Then I can talk about the projective and the injective tensor products of convex bodies. So in the literature, it is known there are a lot of definition of projective and the injective tensor product of different objects. In this case, when you have convex bodies containing the origin in the interior, then the projective tensor product is the convex hull of the simple tensor determined by each of the convex bodies P1 to PL that you are about to multiplicate, something like that. And on the other side, by means of polar sets, we can define their injective tensor product as the polar set of the projective tensor product of the polar of each of the convex bodies having the origin in the interior. So, and direct or straightforward property is that the projective tensor product satisfies a universal property, which is the same that satisfies the algebraic tensor product. And this is the property that tells us that if we have a multilinear map and a convex body having the origin in the interior that are related with P1 to PL by means of this inclusion, then you can linearize this map in a way that the projective tensor product is always contained, the image of the projective tensor product is always contained in the convex body Q. And you have this linearization. So this follows directly from the linearization properties of the algebraic tensor product and from the fact that linear maps preserves convex hull. So if you have, this is a convex set, then it's convex, this convex hull belongs to the set, and then you can play around with this linearization and exchange convex hulls with the map. So that's is the property that determines or characterize the projective tensor products of convex bodies having the origin in the interior, in the sense that if we have another pair of a convex body and a multilinear map with this property, and such that this pair satisfies an analogous property that preserves the corresponding inclusions, then you actually have a bijective linear map between these spaces that sends your convex body P to the projective tensor product, and your canonic and your multilinear map to the canonical one. So let me give you some examples. So if we, on RD, we can fix our standard basis, and the tensor product is, again, an orthonormal basis, and we actually can think, imagine I'm on RD, and I pick one decomposition or factorization of D in natural numbers. So I have this like linear isomorphism between the spaces, and I can define the LP balls determined by this by this decomposition, where here P is greater than 1, and it is the definition of the LP balls. In a similar way, we can do this for the L infinity balls here. So for P strictly greater than 1 and less than 1, we know that the LP balls are actually closed unit balls of reasonable cross norms, independent of or better, in no matter what the composition we use, they always have enough symmetries to be a reasonable cross norm on the corresponding LP spaces. And particularly, if we consider P equals to 1 and P equals to infinity, then we have this relationship with the projective and the injective tensor products. So notice here that this gives rise to a question is, imagine you have a convex body in one RD space. What are the symmetries of these convex bodies that allows us to do things like that once we are seeing here with these convex sets? So now we can define a tensor product of convex bodies in this way. So we say that a tensor product of order L of convex bodies having the origin in the interior is an assignment that takes L tuples of convex bodies and returns a convex body on the tensor product that satisfies two conditions. Or the first one is that it has this relationship with the projective and the injective tensor product. And the second one tells us that for every linear map, if we have this relation between, this is the image of the convex body P, if we have this inclusion, then the whole tensor product satisfies this inclusion. So we can like carry on this inclusion to the tensor products of the space, the tensor product of the convex bodies, and the image of the tensor products of the convex bodies by the tensor products of linear mappings. And this property has direct, but from my point of view, funny consequences. So the first, these are three straightforward consequences. So the first one tells us that if your maps are actually bijective linear maps, then if you send a tensor product of convex bodies P1 to PL by the tensor product of the linear maps, then you obtain the tensor product of the image in each part, in each body. And as a consequence of this property, if at least one of the convex bodies is origin symmetric, then the whole product must be an origin symmetric convex body. And the last one tells us that these products tells us that each tensor product is continuous with respect to the Banach-Mazur distance, which is a property that we would expect to have. So I'm going to sketch the proof for the case L equals 2. And we'll recall that the geometric definition of the Banach-Mazur distance is this one. And this property here is going to be a consequence of the universal property, the uniform property, and this one here. So if we consider lambda and T a bijective linear map such that we have these inclusions, then by the uniform property, we can verify this, and then we can, as a consequence of the previous of one on this proposition, we can express this in this way. Then again, we use uniform property and again proposition 1, and we got these inclusions. So the Banach-Mazur distance between these products, these tensor products, is bounded by the Banach-Mazur distance of the bodies that we are varying. So P1 and Q1. And the whole result then follows from the properties of the multiplicative triangle inequality of the Banach-Mazur distance. So if we begin with this pair of convex bodies, then we can fix one of the convex bodies and vary the other two, and we got this property from the multiplicative triangle inequality, and then we use this result twice. And this is the basic idea. Now, so ellipsoids are fundamental objects when you're working with convex sets on finite dimensions, and also with ellipsoids are fundamental for the theory of Banach spaces. So a natural question is, what about the ellipsoids? What is the relation between ellipsoids and tensor products? So we are going to consider origin symmetric ellipsoids determined by the Euclidean ball of the Hilbert tensor product of these spaces. And you can define the Hilbert tensor product of ellipsoids as the closed unit ball of the corresponding Euclidean spaces. So you are considering here ellipsoids, you have their Minkowski functional, and you have the Euclidean space. You take the tensor product, the Euclidean ball, and you have this is a name for that. So we have a characterization of the ellipsoids that lies between the projective and the injective tensor product of the Euclidean balls. And we proved that we only have one, which is the projective, which is the closed unit ball of the Hilbert tensor product, or the tensor product, the Hilbert tensor product of the Euclidean balls. So here we did we proved the result for fixed ellipsoids here. And if we change the ellipsoids, then what we know is that if we have an ellipsoid that is if we have an ellipsoid that has this property, that is, it lies between the projective and the injective tensor product of some ellipsoids, then it has to be the Hilbert tensor product of the ellipsoids. And another natural question is determined what is the relationship between tensor products of convex sets and its classical Löffner and John ellipsoid. So the Löffner ellipsoid is the ellipsoid of minimal volume containing P, while the John ellipsoid is the ellipsoid of maximal volume contained in P. So we have this result that tells us that under some conditions, this is the condition for the Löffner ellipsoids, and this is the condition for the John ellipsoids. And it tells us that if we have a tensor product of convex bodies with the origin in the interior, then if we assume that our products are related in this way with the Hilbert tensor product, that what this actually means is that if you take a tuple of ellipsoids, then this tensor is contained in this tensor product is contained in the Hilbert tensor product. So if you have this property, then you can show that Löffner ellipsoids of the tensor product is the Hilbert tensor product of the Löffner ellipsoids. And similar for the John ellipsoid when you have this condition here. So the idea of the proof is to use, for the case of the Löffner ellipsoid, is to use, well, the inclusion, this hypothesis guarantees that we have this inclusion. So the projective tensor product is contained in this ellipsoid. So we might expect that this actually will be the Löffner ellipsoid of this body. So we use the composition of the identity by means of contact points between the convex set, its polar, and the Löffner ellipsoid of each of these convex sets. Then we obtain this decomposition for the identity of the tensor. And since Löffner ellipsoids are unique, then we have this equality. So for the John ellipsoid, there's a relationship between these. They are dual to each other. So one is the polar of the other. But that gives or takes us naturally to consider what is the relationship, or what happens, what is the relationship between the operation of taking polars and the operation of taking the tensor products of convex sets. And we can define this a dual tensor product. So if we have a tensor product of convex bodies with the origin in the interior, its dual tensor product is, again, a tensor product that once you have P1 to PL, returns or is defined as the polar set of the tensor product of the polars of the set. So here, what we actually have to check first is that this definition does not depend on the scalar product defined on these spaces. And we have that this is the duality, or we have these duality results that tells you, like, this follows directly from the definition of the projective and injective tensor products. we have one is the dual of the other. So where are they? So here, from this definition, you get that the dual of the projective is the injective tensor product and vice versa. So here. And as occurs with the polar set, with the operation of taking polars, if you take duals twice, then you recover your original tensor product. And this property, again, this inclusion means that if you compare the projective tensor you compare this tensor product of P1 to PL is always contained in the tensor product of P1 to PL. And this property tells us that we actually have this reversing inclusions property. So now, what happened with sections and quotients of these convex sets? So we have, so the question is, if we have a section of the tensor product of the convex sets that is determined by these linear spaces, I mean, it is determined by the tensor product, the algebraic, the tensor product of each of these spaces, which is a linear subspace of this space. So we want to know what happened with, what is the relation between this section and this section over here. So when we have this equality, the sections, this type of sections of the whole of the convex sets are determined or agree with the projective with the tensor product of the sections. We said that our product is injective, and we say that the product is projective if we have if we have T1 to TL surjective linear mappings, then this satisfies this relation. So the image of the tensor product is the product of the images. And we can prove that these properties are dual to each other. So if your tensor product is projective, if and only if it's dual, it's an injective tensor product. Now, we are going to consider only origin symmetric convex bodies. So if we consider origin symmetric convex bodies, you can, in a similar way, define the first property and the uniform property. And notice that from our proposition that tells us that if one of the convex bodies in a product are origin symmetric, then the whole tensor product is origin symmetric, then all of the tensor products of convex bodies having the origin in the interior determines a tensor product of symmetric convex bodies. So from tensor norms to tensor products, we can prove that if we have a tensor product, then in this way, by means of the Minkowski functional, we can define a norm on the tensor product of finite dimensional Banach spaces. And in the theory of tensor norms, you have the concept of dual tensor norm, which is a norm determined by the dual spaces, and you also have the notion of injective and projective tensor norm, which is a tensor norm is injective. This is each of this subspace of the Banach space X satisfies this property. So the tensor product of the subspace is a subspace of the tensor product of the spaces. And this is the corresponding projective tensor norm, projective norm. And you can go from tensor norm to tensor products of symmetric convex bodies, not of symmetric convex bodies. And again, we stay in the finite dimensional context. And then our Minkowski type theorem that preserves the calculus of between these two notions tells us that if we have a tensor product of convex sets, then we can then it determines a tensor norm on finite dimensions, and this is actually a bijection that preserves the calculus, means that these tensor products are dual to each other. The same occurs for their corresponding tensor norms, and the properties of being injective and being injective in both contexts are related in this way. So let me give you an example of what are the type of results we would like to have. So given a tensor product, we can define what we call the smallest injective tensor product that is above our given product. So if we do this for the projective tensor norm, for the projective tensor product, then we have this definition. So the smallest injective tensor product is the intersection of all of these bodies that over taking into account this condition. So we can prove this result that tells us that if we have isometric embeddings from these normed spaces, notice that these are origin symmetric convex bodies, so this is a normed space, and we can show that this tensor product is the inverse image of this finite dimensional section of the projective tensor product of the L infinity spaces. So it's a finite dimensional section of a infinite dimensional convex set. And particularly if we have if P1 to PL are the B infinity balls, but well, we have this equality between the projective, the smallest injective tensor product, and the projective tensor product of the convex set. And the idea of the proof is actually to show this independence of the embeddings. And then by the Minkowski type theorem, it follows that this tensor product of convex sets corresponds to the biggest injective tensor norm. Then for an appropriate embedding, it follows that the smallest injective tensor product is a section of this infinite dimension. It's the preimage of a section of this infinite dimensional convex set. And this is what I wanted to talk to you about today. These are some related works. And this is the work from Maite and I. And thank you, everybody, for attending. Thanks.
Thank you very much, Dr. Higueras. Are there any questions from the audience? I'll go with Volker first.
Thank you for the nice talk. Is there how important is it to use the Euclidean structure of the spaces of the for the building the tensor products? Could you also do it for general Banach spaces with no Hilbert space structure?
Oh, in general, no, because we want to have polars and we want to represent these. We want to have this duality. This duality here. And this duality belongs to the finite dimensional context. And that's the problem to try to if you try to think in these terms in tensor products of convex sets of Banach spaces, then the problem is you don't have polar set. You don't have this property of polarity. Also, if you consider the words compact and sets with interior, then you are restricting your convex bodies to be compatible with the Banach space structure. So here we can play with so we pay a cost because we have to state on finite dimensions, but we can play with different convex sets and we can think that our dimension is growing all the time. In that way, you can recover some of the infinite dimensional ideas because there's a way to given a finite dimensional a finite dimensional tensor norm to define a tensor norm on the product on infinite dimensions, but we like polars when we are restricted to the finite dimensional setting.
Thank you, Luisa, for your very beautiful talk. I have a question, an naive question. What happens if you consider more general symmetries instead of taking only the symmetries given by the origin, maybe a symmetry given by a subspace? What happens in Minkowski theorems if you consider this?
So the symmetric part is important because the origin symmetric part, it is important in terms of the Minkowski theorem, but because we want to represent the space, we want to have the space and their dual. However, there are some extensions of the notion of polar sets when you do not require to be an origin symmetric convex body, but we haven't explored that part.
Thank you.
So I have where the necessity to talk about these different tensor products arise. I mean, you have already tensor product in the space, I mean, in the vector spaces, and then you want to have a notion on convex spaces, and it happens that there are many notions and they have different properties. And so why, I mean, what is the need of that? How it arises? Also, I was looking at you passed very fast the literature, the bibliography. There is one in the previous one, Physical Review A. I mean, it's kind of, probably there is a reason why the people are doing that, because
Yeah, there's a lot of applications of tensor products in the context of quantum computing, and one of the interests is to determine some quantitative values of some convex bodies that arise in this context. So the convex bodies that are used frequently are the projective and the injective one. And this is the same for the theory of Banach spaces, because one is essentially one is a convex hull, which you can imagine, you can understand relatively easy because it is a convex hull, and the other is it is a dual of a convex hull. So the idea behind to work with this is that if we explore more quantitative properties like relation with Banach-Mazur distances or properties of these convex sets, well, maybe we can produce some interesting results in this context. And this is what they did here, actually.
Okay, if that's all the questions, I think that was a good discussion there. And thank you very much, Luisa. And I hope that we can take 2 minutes just to whatever you have to do.
Thank you.